Hello, welcome to our channel again. Suraj here with a new video of mine. And today I'm going to discuss a topic, which is the topic of the modern physics, which is a Compton scattering. Okay, so what exactly this particular thing is, and there's also a formula which is used to govern this scattering, or you can say that a Compton shift. So what's the Compton shift and scattering? We all are going to discuss in this particular video. So this is generally the section of a modern physics, and generally it's the particle nature of light wave, which is photons. It means in this particular experiment, we are dealing with the photon as a wave, sorry, as a particle, not as a wave, because what the experiments did with this particular Compton scattering effect is different if we imagine the wave nature of the photon. So I will make a video on that. What will happen if we try to explain the Compton scattering with the wave nature of the electron, sorry, photon. So if there is a wave nature of the photon and you start doing some calculations on the Compton scattering, you will find out that this particular wave nature of a photon is not exactly matching with the experimental observes. Experimental, if you do experiments and you will observe something of Compton scattering, the particle nature of light explains it in a very beautiful way, not the wave nature of light. That's why this particular Compton scattering is generally when we deal with photon as a particle, not as a wave. But as you can see that here in the diagram, I've made photon as wave. So this is not a wave. Please do not misunderstand this particular thing. I just trying to make the diagram look something beautiful. That's why I made a wave instead of a particle. But remember, always Compton scattering, you deal with photons, you will exhibit the particle nature of light of the photon, not any of the wave nature of the light of the photon. The diagram that wave nature I have shown is not exactly correct, but I have made it to make it distinguished from the electron, because if I met two particles, then it's might get very messy to understand the diagram. So to understand the diagram perfectly, I have made here the wave structure. But again, I'm saying Compton scattering is all about the particle nature of the photon or the light. Okay. So here, first of all, before starting the topic, let's understand that what exactly the Compton scattering is. So first of all, we are trying to understand that what exactly is that particular experiment. So in this experiment, it is like the collisions of the two particles we study in the classical physics, and but it's very different from the classical physics. But the calculation that we are going to do here is related with the classical physics, like the conservation of energy and the conservation of momentum. But again, I'm here saying that we have to add the relativistic effect. Why relativistic effect? Because the speed here are very high, and you know that if the speed is very, very high, you have to change the expression of the kinetic energy, you have to change the expression of your momentum, you have to change the expression of your total energy and all that things. There is an additional factor came out, all that things. So that's why this particular phenomena is a relativistic phenomena. And I will also make a video on the different types of the relativistic quantities, and also why there is a use of the relativistic quantities. But for now, we have to understand this particular experiment, and I'm here use the different types of the relativistic equations also. So first of all, let's understand what this experiment is. So in this experiment, what happened is that we will have to check out that what will happen if we to try to do a collision between a photon and the electron. So this particular Compton scattering phenomena is explained well by the particle nature than the wave nature of light. And the fact that why there is no any type of the wave nature here photon, it means that why using the wave nature is not accurately correct, is not correct, then what's here going on? Why we have to imagine the particle nature of the light in this particular Compton scattering? So the answer to this question, I will make a video, because it's a very good to know that why, if we imagine there is a wave, not like a discrete quanta photons, then what will happen to this particular experiment? I will make a video, and probably the next video will be on this particular, that why wave nature is not there in the Compton scattering. So for now, let's study that what is going here. So if you see, if there is a photon and the photon is a particle, and if you do the collision between the photon and the electron, this is a scenario of the collision. And after collision, what will happen is that maybe the electron started moving here, or let's say photon started here. Let's here say, let's make a photon. Okay, so this is a photon P, and the electron started moving in this particular direction. This is our particular electron, and this is our path of the electron, and after collision this happens. So after collision the photon makes some theta angle, and after collision the electron makes some phi angle. Now here, if you all know, we're familiar with the equation of the energy of a photon, it is equals to the h mu, where we use the frequency. It's not the velocity, it's the sign of a frequency. So it means before collision, the energy of the photon is h mu, and after collision, we all know that some of the photon energy get transferred to the electron, and that's why electrons started moving. So it means now there is a decrease in the energy of the photon, and energy is directly proportional to the frequency. It means now the frequency of the light decreases, and let's say the decreases frequency as mu naught, mu dash. So this is h mu dash. And after this, some of the energy is gained by the electron, and electrons started moving. And this is a phenomenon of the Compton scattering. So what essentially we have to do is here to derive the expression that how much wavelength shift. That's why sometimes it's called the Compton shift. So what we have to do is that we have to derive a particular formula, which is a very famous formula, to know that how much amount there is a change in the wavelength of the photon. And that is the formula we are going to derive. The change in photon wavelength after striking to the electron. And that's all we have to do. So let's start the calculation. So first of all, you have to derive that energy. So energy of a photon, we all know that is equals to the h mu. And this is the before collision I am taking. So before collision energy of a photon is h mu, and before collision we all know that electron also has some sorts of energy which is called the rest mass energy, which is equals to the mass of the electron, rest mass into the c square. It means the energy of the electron is equals to the mec square, where me is the mass of the electron. But after collision, what will happen is that the energy of the photon is now h mu dash. It changes, it decreases. And after this, we all know that there is also the energy of the electron. So we have to find out what's the energy of the electron. So energy of electron is essentially root under, it is a very famous formula, me square c4 plus p square c square. So this will be the energy of a electron. And in the case of the light, it's with zero rest mass. This term blows out to zero, and that's why you see everywhere the formula of energy of a photon also as E is equals to the Pc. Okay, this is what essentially formalized. But the electron has a rest mass. That's why for electron, this terms do not vanish. And here E is equals to root under me square, where me means the mass of the electron, c to the power 4 plus p square and c square, and this is all in the root under. So now, what happens to the momentum? So let's apply the conservation of momentum here. We have to derive a particular formula. So let's apply, we will use both conservation of momentum and conservation of energy to derive the expression in the change in wavelength of a photon while collision, after collision. So here the conservation of momentum is like in the vector form we are writing. Let's P, which is the momentum of the electron before and after, the momentum of the electron is P dash, which essentially with also the momentum of the electron. So this is the conservation of the momentum that before collision P here is the momentum of a photon, and after this is the momentum of photon, and this is the momentum of the electron in the vector form. So how can I write the momentum of electron in a vector form? So momentum of electron in vector form is equals to the momentum of photon before collision minus momentum of photon after collision. Okay, that's right. That's pretty simple. Now what we have to do is that we'll find out the magnitude of this particular quantity, which is the momentum of the electron. So after magnitude, we means P E squared which is equals to the p square. I'm removing the here arrow because now it's all about the magnitude, no any type of direction. That's why I am removing the arrow. Do not get confused. P square plus p dash square minus 2p p dash cos theta. Okay, so here is our particular formula of the magnitude square of our electron momentum. So we are going to use this particular formula. So this formula is going to be quite very useful in our expression when we do the conservation of energy to sort out a particular formula. So now let's use the conservation of energy. So conservation of energy is like that. I will make a diagram here to make it clear. This is the incident. After this, in this direction, this is HV dash. This is H mu. Sorry, V no mu. Okay, and here is the direction of the electron, which is its energy. This is the theta angle, and this is the phi. Okay, so here is the photon, and here is the electron. So let's apply the conservation of energy. So before collision, the energy is of the energy of a photon, which is simple, hc upon lambda. I've changed because the frequency is equals to c upon lambda, so I put here hc upon lambda, okay, which and plus the energy, rest energy of the electron, which is equals to the mec square. And after collision, the energy of the photon is hc upon lambda dash. And we all know that after this, the energy of a electron is me square c4 plus p square and c square. Now I will take this particular in the left hand side, which become hc upon lambda minus hc upon lambda dash and plus me c square is equals to the root under me square c square plus p square and c square and root is over. Okay, now what we can do is that we can take a squaring on both sides. So before squaring, I will take common hc here, which is 1 upon lambda minus 1 upon lambda dash plus me c square, and it's essentially equals to the root under of me square c, sorry, it's not c square, the c4, a small mistake here which can cause big trouble. Okay, c4, and it is c4 plus p square and c square. Now if you do the squaring on the both side, so I will do the square on both side, squaring and squaring. Let's see what will happen. It will become h square c square 1 upon lambda minus 1 upon lambda dash square plus me square c square and plus here 2 into h c cube m e 1 upon lambda minus 1 upon lambda dash. So this is whole left hand side. Now what is right hand side? So this particular is equals to the one. So on right hand side we can write this particular, okay, so this thing we are going to write here is equals to the me square c4 and plus p square c square. Now we have to simplify this. So what we can do here? Okay, so let me see what we can do. So here h square c square 1 upon lambda square minus 1 upon lambda dash square, sorry, a plus, minus 1 over lambda into lambda dash. Okay, that's fine. And plus me square and c square, where me means the mass of the electron, do not get confused. hc cube me 1 upon lambda minus 1 upon lambda dash. And this certainly equals to the me square c4 plus p square and c square. Now, we are going to, here p is the momentum of the electron, and now we are going to plug down the value of the momentum of the electron, and let's see what we'll get. So h square c square upon lambda square plus s square c square divided by lambda dash square and minus h square c square divided by lambda into lambda dash, and plus here it's me square c square, oh sorry, it's c4 not a square. Okay, what I'm doing, so it's m square c4 m square c4. Okay, ignore mistakes, sorry for this. For 2 hc cube me 1 upon lambda minus 1 upon lambda dash is equals to the me square c4 plus pe square and c square. So I will put down the value of the p square which we derived here, this particular term, and we are going to plug down the value here. So I think the equation will be very long, but okay. H square c square l square plus h square c square upon l dash square minus h square c square divided by lambda dash plus me square c4. Okay, so we can cut this out. Okay, so this and this term vanishes. Okay, now the equation started. Okay, now we can write this particular expression as 2hc cube. 1 minute, let's see the rate of mistakes. No mistakes. Okay, now me 1 upon lambda minus 1 upon lambda dash. Now what's the value of here? P squared. So it is equals to the momentum. Okay, no arrow because it will make very messy. Okay, so P square plus P dash square plus 2p P dash cos theta. Okay, and into obviously into c square. Okay, so here p square is the momentum of the photon, and this is of the photon. This is after the striking the momentum of the photon. So now what essentially we can do is, okay, so here h square c square upon l square plus h square c square upon l dash square minus h square c square upon L into L dash. Okay, L into L dash plus 2hc cube me 1 over lambda minus 1 over lambda dash. It is equals to the, what's the momentum of the photon? So the momentum of the photon is a very famous formula, so where I can write it. Okay, so if you remember, then the momentum, here I am writing this. Okay, so momentum of the photon is equals to the energy divided by c, and that p is energy. What's energy? Energy is h mu upon c. Okay, that's fine. So let's put down the value of here, which means it become h square mu square divided by c square plus h square mu square divided by c square plus, okay, no, plus, no, minus, I think. Oh, what type of mistakes I'm doing. Sure, it should be minus, not plus. Okay, no problem. So, okay, so it's minus, and here's also minus 2h square c, sorry, not c, mu. It's mu square divided by c square, and in the bracket it's c square. So the c square and c square get cancelled. So let's write it in a more compact manner. Okay, it's h square, and if you remember, that's c square upon l square is mu square. So let's write it as, 1 minute. Okay, it's h square, and the c square upon l square is the mu square generally. So it's like mu square plus h square mu dash square. It means it should be a dash. Okay, dash square, and negative of h square c square divided by lambda into the lambda dash plus 2hc cube mass of electron into 1 upon lambda minus 1 upon lambda dash. And this expression, if c square and c square gets cut out, it is equals to the h square mu square plus h square mu dash square minus 2h square mu square. I think it's mu, no, no mu square, because these two frequencies are different. You can't do this. Two frequencies are different. Sorry for this. So it's mu into mu dash. So it's mu into the mu dash. Oh gosh, this gets cut out. This also, and this also gets cut out. Now what we can essentially do is that h square. Okay, now we have negative of h square c square divided by lambda into lambda dash, and it's plus 2h c cube me 1 upon lambda minus 1 upon lambda dash, which is certainly equals to the negative of 2h square mu into the mu dash. Okay, so next what we can do. Okay, so to simplify this, I I'm using new thing which is blue. Okay, so using this, we can take this as 2h c cube me, and here if I take the lambda dash minus lambda, sorry here, lambda dash minus lambda divided by lambda into lambda dash is equals to the h square c square divided by lambda into lambda dash, and it's negative of 2h square v into v, which is mu into mu dash, which is frequency. Okay, now if I take h square common and cut out the h squared, it's look like this: 2c cube, okay, me lambda dash minus lambda and divided by lambda into lambda dash, and this certainly equals to the h square c square divided by lambda into lambda dash negative of 2h square. So what is her frequency? So this from basic formula, which is lambda is equals to c upon mu, which is frequency. You can put a mu as c upon lambda, which means this particular expression become c square and divided by lambda into lambda dash. Okay, and here h is missing, I think. So let's put h here. Okay. Now, if I cut out the h, what will happen? The equation become 2c cube me lambda dash minus lambda divided by lambda into lambda dash, and one h from here also, which is hc square minus 2hc square, and if I take here as lambda into lambda dash. Okay, is there any mistake here? Let's see. Minus, okay, okay, this minus became plus. So if I cut out this particular, this and this, and also c square, again I found another, I find a missing term, which is here cos theta. Oh, uh, I haven't written here the cos theta term. Okay, but no problem, put it here, cos theta, no problem, cos theta, cos theta, cos theta. Okay, here it is also cos theta. So here is also cos theta. Now if I cut out here also c, it become 2c me, which is mass of the electron, and lambda dash minus lambda is equals to the, this will become h common and 1 minus 2 cos theta. Okay. Now if I take 2 here, it means now lambda dash minus lambda is equals to the h divided by 2c me 1 minus 2 cos theta. Okay, so here I found a mistake that 2 is missing here. Sorry for these my small mistakes. So it will become 2 here. This is 2. I'll make sure that in my next video I will just try to improve my mistakes. So this will become 2, and that's why I thought that how this extra 2 is coming here. So now what our equation can be written as. Oh God. Okay, no problem. So this is divided by lambda. Okay, so it's this lambda and this lambda gets cut out. That's all what's written here. And if I take 2 also common, this 2 and 2 will also cut out. C square and C cube cuts out, and the equation is C ME and lambda dash minus lambda dash minus lambda is equals to the, if I take h common here, it will become 1 minus cos theta. And then the Compton shift, which is a shift in the wavelength, that how much wavelengths get shift is this particular quantity, which is lambda dash minus lambda, where lambda is the original wavelength before the collision, and this is the wavelength after collision. As you know that if the energy decreases, then the wavelength increases, and that's why lambda dash is bigger than lambda. And this is h upon MEC. E is just a subscript, not a E, like MEC 1 minus cos theta. Okay, so this is the shift in the wavelength of the photon. Where remember that angle theta is the angle of the incident photon, angle between the incident photon and this particular photon after the collision. So this is all about my video on the Compton scattering. Hope that you find it helpful. As I've done a lot of small mistakes, but after this I corrected all of the mistakes. But if you find any other types of the mistake in this particular video, you can comment any type of mistakes. And this is a video on the Compton shift. In next video, I will try to make that what's the wrong with the wave nature to depict the phenomena of the Compton shift and all of this particular thing. And also I've started a series of the black body radiation, and maybe in 1 to 2 days I will try to upload the Rayleigh-Jeans law and how to obtain the Rayleigh-Jeans law. And after this, eventually the Planck radiation law, which is a very important law in the black body radiation. And in the quantum statistics, we will also find the use of the Planck radiation law. So as I have said before that I'm gonna start the statistical physics. So there's two is physics, which is Maxwell-Boltzmann statistics, and the quantum statistics, which is the Bose-Einstein. So mainly we are going to focus on the Maxwell-Boltzmann statistics because it is what we are going to study in the astrophysics in the major section. But yes, quantum statistics is also very important, and I will also try to make a video on that particular topic. So this is all on the Compton scattering, and if you have any doubt related to this particular topic and in physics, you can comment down your doubts. So that's all for this video. Thank you.